Um, I will try it without the microphone. I think I'm loud and clear. Is it okay? Perfect. Then I will just take the
I think
pointer.
they're also recording this to encourage us to use the
To the benefit of
Okay. Then no problem. Then we
Yes,
have two
so-
things in my hand.
Yeah.
That's it. Hello. So welcome everyone to this nice conference. We had a very good plenary session, and now I'm very honored to start the conference or to open this session from my presentation on the topic of air pollution prediction using machine learning techniques, a concept to replace the existing monitoring stations with virtual monitoring stations. My name is Abdul. I'm a research student at the University of Stuttgart in Germany, and this will be my research work. Perfect. So first of all, I would discuss something about the air pollution and its harmful effects. Um, as we all know, that air pollution is mentioned as a silent killer, and also in WHO, it has been published that around 7 million premature deaths can be traced back to air pollution annually worldwide, and also it is an important aspect of urban climate. Air quality in the cities is usually poor, as we all know, and most of the population also live in cities and they are exposed to this population. So this shows the impact or the importance of air quality in urban climate. The parameters that affect the air quality are meteorological parameters such as air temperature, wind speed, solar radiation, precipitations, and so on. Thermal wind systems, and also the local emission sources such as traffic, combustion processes, and so on. So, to understand this concept, this is very important to measure the air quality. And I have brought with me the example of the city of Stuttgart in Germany, which has around 630,000 inhabitants and an area of a little bit more than 200 kilometer square. And you can see here in the whole Stuttgart city, we have only 5 official monitoring stations that measure the air quality. So the reason being, the measurement devices are expensive and the regular maintenance is required. And the problem is that such less number of monitoring stations do not provide the spatial information on air pollutants, and therefore mobile measurements and low-cost sensor networks can be used to improve this spatial distribution of air quality measurements. And urban climate models can also be used to simulate pollutant concentrations on a larger scale. But another method can be that machine learning techniques can be applied to estimate the pollutant concentrations. So, summarize the first two slides that I have just showed for the people that came also later. We have a problem that the data that is available on weather and climate is limited, and it is not spatially adequate. And then there is hardly any air pollutant concentration prediction using machine learning that can complement the existing monitoring stations. A solution can be that we collect extensively the data to train, test, and validate the models that we use, and also that we develop a technique, a machine learning model, for example, that uses this data and that can serve as a simulated monitoring station, and then they can complement the existing monitoring stations that are already measuring the air quality. So this was done in this research study, and the methodology has been shown here graphically. What you can see, as I mentioned before, the data is air quality data is measured, also the meteorological data, and all this data is used as an input for machine learning models. The input data that we used was meteorological data, air quality data, traffic data, and the data from the air quality network that has been measuring the machine learning models that were used in this research. They were selected on the basis of the literature review that was done. We used ridge regression, score vector regression, random forest, X-tree regression, and XGBoost, and all of that was done compared with the real data. And the performance was measured by R square value, mean absolute error, mean absolute percentage error, and mean squared error. So the scenarios that were done, it was the model was developed from very basic, simple one, and then it was complexified later on. So the first of all, only the meteorological data was considered as input in scenario one. In scenario two, the existing meteorological data and then the traffic data was introduced. Then it was the scenario 2 data was again given another input, that is the pollutant from one station measuring nearby. And then another scenario was considered in which the input data from scenario 2 was enhanced with the pollutants from the nearby stations. All of this was and the outputs were considered. So the input data from these four scenarios was considered individually, and then the models were applied, machine learning models on this data, and then all five models that I mentioned in the previous slide, the output were tested or was shown individually, as well as an average. So the later on the results would be shown would be an average of all these five models, and then the maximum and minimum of these models will also be shown. So that's how the results were presented. The pollutants that were discussed or were of interest were PM2.5, PM10, and nitrogen dioxide. The locations, as I mentioned, it is close to, just to give you an idea. So the first location was somewhere here, Marienplatz. This was the station from our department, close to the official measuring station, and the second location was Neckartor here somewhere. So there is a difference of around 4 to 5 kilometers if you move from these two stations. And the time, the training and testing data time was from the training data set was from the time of 2018 start until the 31st March 2021, and then the test data was complete 1 year from April until March 2022. So the first results, these are the results of the R square metric and the error metric for the mean absolute error and root mean square error. And you can see for the pollutants PM2.5, PM10, and nitrogen dioxide at one location. This is the first location, Marienplatz, with our own measurement station, and this is the scenario 4, and you can see the difference. The R square values in the first scenario, which is just the meteorological data, very simple model, the R square values are very low as compared to the scenario 4. PM 2.5 has even the R square values above 90%, then around 80% for PM10, and the NO2 more than uh, between 70 to 80%. And the errors are also reduced in scenario 4. So the complex scenario, the more inputs you give, the better results you get. To show you a temporal resolution, the results in the next slides will be presented like this. So I will be explaining one result. So on the x-axis, you have the timeline. On the y-axis, the pollutant, and the actual concentration that we measured with the monitoring station during the time. This is the test data time period. It is shown with the red line, and the average is the model data or the data that is being obtained from the machine learning model, that is the black one. Then the minimum and the maximum are shown with blue and green color respectively. So this is for the scenario 1 at one location at Marienplatz, and here you can see the scenario 1, very simple one, and yeah, the real values and the model values are very far away from each other. In scenario 2, the addition of traffic data was done, but we thought that there would be a very huge improvement. But still, you see, there is not much improvement from scenario 1. In scenario 3, the data from one pollutant from another station was added, and you see there is an increase in the comparison of both the model and the predicted, the real values. And the scenario 4, which was the best of the case, and here the prediction and the real values really coincided with each other, was shown here in scenario 4. So this is not only on one location, we checked that on another location, and we got the similar results. So this is at Am Neckartor, Stuttgart, the results, and then here similar results were seen for PM2.5. Then I move to the next results. Here again, the magnified result for scenario 4. You see the actual values and the model average values are very much coinciding with each other, with some exceptions here. The similar results were obtained for PM10. The PM2.5 results for scenario 4 were very much coinciding with each other. Here we had some session of PM10 results in which some discrepancy can be seen, but overall, as a whole, the results are coinciding with the real values. Similar to the other location, the PM10 results, they are very close to the real values. And then, since I have 1 minute left, so identical results for NO2, and then I move to the one more application that we did. Since it was on one location, the idea was to generalize it, and then if this technique can be used to any other location. So we found another location with a similar data set. This is another city near Stuttgart. This is Karlsruhe, almost a distance of around 75 to 80 kilometers away from that. And a similar technique was applied. And here you can see only the scenario 4 was considered, as it showed the best results. And this was applied for PM2.5, PM10, and NO2 concentrations. And here you can see the R square values around 90% for this machine learning model. So to conclude, I would say the field measurements are an important data set that can be used for individual as well as for model validation. And then this developed model, the machine learning model to predict the pollutant concentration, showed a decent generalizing ability in the prediction. And the pollutants from other monitoring stations, the scenario 4, played the significant role. This showed the best results. And as you have seen in the last slide, so this developed technique was applied to the other location and showed promising results. So the concept is that this methodology can replace the existing monitoring station. So if you measure at one location for a certain period of time, you have this training data, and then you have this model, and then you can replace this existing station to another location, and then this simulation monitoring station, this can continue the results for that, and then you can have a high spatial distribution in a measured area. So that's all from my side. This research has also been published in Atmospheric Environment. If someone is interested, they can scan the QR code. I will also be presenting a poster tomorrow, so if you want to know how the data was obtained, so you can also visit the poster, and for further questions, I will be glad to answer. Thank you very much.
We are unfortunately a little bit tight on time, so if you have questions for Abdul, could you hang out and do this at the end, because we're already 1 minute into the next talk. I'm so sorry.
No problem.